Guess I might as well start. I would apologize that on the schedule it says I'm from JPL, which is true, but that's one hat. My other hat is I'm a postdoc at USC, and this work is actually coming out of there. Need to update my Linux Foundation profile. Cool to see some interest. I was surprised this talk even got in. It's very much on the outside of things that happen here, but hopefully A, interesting just because it's interesting, and B, definitely develop opportunities here. There's a lot of potential for drones in science that as of yet is mostly untapped. So yeah, I'll give you some context, what's getting used, how expensive it is at the moment, and then talk about where I think things potentially could go. Basically that drones should be as regularly used in the sciences as we use our multimeters. There's huge potential for them, but you got to teach or make it easy to use by non-engineers is my hypothesis. So they have been being used for at least the last decade, but mostly as very large, expensive, big tools that require a whole team of engineers and probably a decade of development before you even get your first image out of it. I quite like this flow of showing where UAVs fit in the remote sensing world, all the way up from a satellite, which, I mean, that pixel looks useless, but when satellite imagery is hugely useful. But compared to 2.5 meter or say 4 centimeter resolution that we can get with a drone, and never mind the potential of satellite, you get a cloudy day, well, you get a cloudy image. Drone, you fly below the clouds, you can fly today, tomorrow, and you don't have to wait a week, a month for the next satellite pass, et cetera, et cetera. So plenty of advantages for drones. Outside of that, just outside of the sensing, lower environmental impact, if I can sense something without traipsing across the land or having to launch an icebreaker into the Antarctic, if I can go into a cave, that's instead of having a trained spelunker, I can just send a drone down there. Probably the biggest advantage, though, is temporal and spatial resolution. So obviously, spatial resolution, I can get much higher res imagery or sensing, but the repeatability aspect, that I'm not waiting for a satellite or I'm not waiting for another $1 million grant to launch another year-long campaign with sensors, huge, huge advantage that opens many doors in science that not novel doors, they're just practically and economically infeasible at the moment. Other practical things, you don't have to send a human down to the edge of a volcano. You don't have to send a human into dangerous ice, water zones, and then cost saving. So some cool stuff that is being done. This is a drone that is on the thousands of dollars spectra, but not millions of dollars. Cool project. The guy from University of Costa Rica who actually did a postdoc at NASA Ames, hence the connection, doing two things. So he's measuring gas emissions above volcanoes in Costa Rica. First, to monitor the state of the volcano. Big question in science, can we predict when the volcano is going to blow? But second, to validate satellite instrumentation out there already. 100 kilogram payload, that's pretty good, but yeah, this is a big drone. On a slightly smaller scale, a friend of mine working in Alaska and New Zealand monitoring glaciers with a Phantom. And this is more where I'm talking, we can do some cool stuff with these small drones, but I like his quote, this is off his blog, single-handedly created data management nightmare. He did a back-end calculation, one flight, he's gonna end up with 6 terabytes of data. So big question there is how do we manage this stuff, because our scientists are notorious for not managing data very well. But plenty of applications in the polar regions which are expensive and dangerous to monitor as it is. Quantify glaciers, quantify ice sheets, monitor the ablation zones of glaciers, which is where the ice starts breaking off into the water, a very dangerous area to go in even with a ship. Wildlife tracking, image recognition, machine learning, how many penguins are there, how many seals. I'm sure you guys have seen some cool clips of monitoring whales from there. Mapping, obviously. Agriculture, this is something they can do with a satellite already, the imagery I'm showing you, but 19 to 29% of greenhouse gas emissions, agriculture. bunch of regulations coming in. How do we mitigate that? And then if we can mitigate it, how do you check whether your mitigation missions even work? At the moment, you stand around in a field for 20 minutes in 10 different places with a little gas chamber. And this is what I'm proposing is, this is my science excuse for doing it. I'm working with a student who is doing this standing around in fields, and we want to try and fly a bunch of gas sensors, integrate that with Landsat and ground-based data input, fuse it, and get a pipeline that people can just fly a simple gas sensor and get a statistically reasonable number. If you can do that, then you can do hundreds of fields in a day instead of maybe 2. So many other applications, 3D modeling, monitor after some sort of disaster. This guy was monitoring after a flooding event. That just shows the movement of soil. He had a pre and post, not those 2 images, the top image. But again, use image recognition. How many trees are down? This color infrared image at the bottom was looking for an algae bloom. There wasn't one, but you can't really see it. In a full zoomed in version of that image, you can detect 4 centimeter algae, I don't know, units in that dam. Yeah, so volumetric measurements, quantify a landslide, quantify forest biomass, various things you can do with infrared. Elevation, this was generate a 3D model and then plug it into a computational flooding model, and now you can visualize what that actually looks like. I mentioned caves or crevasses. If you fly an automated drone down there, not send a human down. Then this last one, I really like, boundary layer atmospheric conditions capture. This comes a guy at Oregon State, took an iris, strapped a 100-foot long strip of temperature sensors onto it, and just flew for like 5 hours. He got his grad students to rapidly change the batteries and got a continuous temperature profile as the sun rose. Apparently very important scientifically, but at the moment, how do you do that with a tower? You can imagine the cost difference. So that kind of thing is what I'm pushing, that there is so much that can be done with an Iris, a Phantom, anything off the shelf, $2,000 max drone, but there are some limitations, and that's what I'm going to talk about in terms of developing. Currently, that's a Global Hawk, $130 million each. Amazing. It can fly across the Atlantic Ocean, all on its own and back, super robust, can carry a 7,000 kilogram payload. But yeah, look at that money and however many years it took to develop, decades, and limited flexibility by flexibility I mean in terms of prototyping or trying new novel ideas. It was made to do X, Y, and Z, and it can do those really well, but that's it. If I have a cool idea, good luck. Yeah, this again just shows how the type of drone I'm talking about. So the USGS, US Geological Survey, which is probably the biggest US organization capturing drone data for science, that's their fleet as of 2009. They've got some new ones. And obviously their systems can fly at 400 feet or whatever, but that's not what they were designed for. They're again, these big, expensive, $3,000 an hour to operate. Great if you have a couple $1 million grant. So what am I talking about? Pro maker style drones. Drones should be a standard tool in every Earth scientist's toolbox. And they could be, if we can help Earth scientists use them, if we can do the engineering in a modular, reusable, easily accessible manner. So if we can do that, then now we take these cheap off-the-shelf drones, and now I can do rapid, highly adaptive, innovative science. I come up with an idea, and 2 weeks later I'm flying. Obviously I come out of this environment. I love the GitHub pro maker style is the best term I could come for. What do we call the the rapid turnover, come up with an idea, see what happens, ditch it, go with it, way we operate, I don't know. But if we can put that into drones for science. I mentioned a high degree of automated quality control. So maker stuff's cool, but this actually needs to be generating data that is of professional quality. It needs to have good provenance so that you write a paper about it, somebody can go back and say, what quality was that sensor? Did you manage your data correctly? Is this actually a true result? But a lot of that you can automate. If you put in the correct standards, if you put in the correct tools, think ERC checker, we can automate a lot of that professional step. So loads of the problems of using drones, like what, the last 3-5 years, drone code stuff has solved the problems. Autopilots solve problem for all intents and purposes. We have the open standard communications, mission planning, developer APIs, it's all there. It just needs to be pushed that pro level. So the big problem is that data standards, scientific community wants provenance. You need good quality metadata, you need standard data formats, you need DOIs, referenceable data. All this data that you collect needs to be interoperable. Can I use it with my satellite data? Can I use it with my ocean glider data? Or I already have a sensor web out there. Can I stick it into or take into a computational model as a initialization? Or can I use that same data to validate the model? I've run the model, now I fly and get real data. Needs to be accessible, searchable, discoverable. I don't know if anybody here, one of my hats is big data. So I don't know if anybody knows what Apache Tika is. It's a document parser that you feed in near any format and it will scrape it for the correct metadata and put it into a searchable database for you. That's just a visualization of the code. All of those, even the little circles, are different parsers, so different document types. It's a mess already, and there's that many, but we need to do that for drones. So this is what I've been building as a side project, the maker bit, is to try and build a platform that would make it easy for a neuroscientist who doesn't have an engineering team to take an iris, strap on a Pi or a beagleboard or whatever, and plug in a sensor. Now, they don't want to know what RS-232 is, or I2 squared is, or even what apt-get is, if they can help it. They probably know a bit about data and analytics, so maybe can write a script in terms of how they pass that data, but really they'd like plug and play, and here's the Velcro, stick it on and fly. There's a spectrum of what's possible within that range, but I think we can go a long way towards enabling that. So start with use Snappy. Not because it's the best option out there, but because of their app environment, for want of a better word. I want to make a greenhouse gas emissions snap, structure from motion snap, DEM snap, volumetric quantification snap. Minor configurations required for this is my no, not even this is my sensor. I'm quantifying ice, not mud or whatever. But for the most part, a lot of this can be automated. It's Snappy, it's Ubuntu, the tools are all there, security's built in. Any platform anybody's ported Snappy to, it can go with. So I don't want to tie anybody to an iris with Pi. I'm potentially tying them to something with a drone code autopilot, but even that's quite a wide spectrum. So within Snappy, my app, ROS, pub/sub, feedback loop designed. So now I have my gas sensor plugging in data, and it's relatively trivial to I'll show you, I plug it into a database, but relatively trivial to write some sort of script that searches for, okay, so you pass, I don't know, 600 ppm threshold. If you see this, do a vertical profile, change your mission, feed it back to the autopilot, stop flying the laps you were flying, and do this. I can integrate multiple sensors, so I'm taking imagery. If I have a slightly more sophisticated board, say a Jetson with a GPU on it, I can do real-time image analysis and integrate my sensor data and do even more complicated auto adjustments on the fly. Really interested in Tuli's talk from Ross yesterday, talking about standardizing some of the Ross message protocols or schemas for drones. So it'll be cool to see where that goes. Problem with most of my ideas is Snappy, Ross is very mature, and some of the tools they're just getting there. So I'm bumping into a lot of it will be there in like 2 months' time things. But yeah, Ross is super mature, and in fact, I heard that DJI is planning to have a snap on their drones as well. So I mentioned plug-and-play ability. Scientists don't want to know what I2C is. There's another project actually coming out of the science community that's building a sensor registry. So it's Earth science sensors, but it's going to be machine queryable. They're encouraging the manufacturers to submit the sensor metadata to this registry such that I can plug in my Pi with my greenhouse gas emissions, snap on it. It will go off to this registry, say, what is this sensor? How do I calibrate it? What are its ranges? Et cetera, pulls that all back in. Now that metadata is saved with the data as I capture it. And it is basically plug and play. It will require community development of, okay, so you have the CO2 meter XYZ, uses I2C, and these are the commands you need to send. But once you build that, not even a driver, once that script, then anybody can use that. And again, that script will end up in this registry. But it's not just for the instruments, so this project's obviously bigger than anything I'm proposing. They want it, so the instruments can query this registry themselves, but also so that a data broker or data store that receives data from X sensor can go and say, well, the sensor provider didn't provide the data, what is this? Or cloud analytics tools, they need to know what the calibration range of that sensor was. So it's a multi-purpose project, but super useful for me. I can plug in my Pi and get the metadata for the sensor I've plugged in. I mentioned I want to shove this data into a database, and then I can search it. Again, this is about integrating different types of data. So if I have a MongoDB on the drone, my methane measurements or whatever will pile into that, and on the fly I can have a script looking for a certain threshold or looking for certain threshold over time. MongoDB is a document store. NoSQL is just a better fit for what I'm trying to do. The schemaless, or dynamic schema design, it just works better, and they have really good support for GeoJSON. GeoJSON not necessarily being the best, and unfortunately not being commonly used in the earth sciences. It's growing, it's just too new, and earth sciences are a couple of years behind whatever the leading edge of tech is. Unfortunately, a lot of the standards that are used in this field are actually XML based, but XML on a Pi, it's a bit heavy. Doable, but anyways. So one of the barriers I'm hitting up against, the current release candidate, this might not even be a release candidate actually, has some ARM support in it for Mongo, but it's not yet in the official distribution, so I can't yet release my Snap with that in it, but it's coming, there's people working on it. Yeah. So I was really hoping to show you some pretty graphs of CO2 emissions over some agricultural fields, but unfortunately the FAA considers scientific drone flying as a commercial operation or whatever. You need the same exemptions that a commercial body needs, which I personally don't have. I am booked to fly with a commercial company that does have it, but that's next month. So, and yeah. So unfortunately, those results weren't quite ready. I was hoping they'd be here, but the farmers, we trying to time our flights with farming fertilization periods, and they only fertilize next month, so I don't have anything. But in theory, it's all ready to go, and I'm using an iris for, it's what I have. No special reason. Some other bits, so I'm solving the on the drone bit. Some other bits that do need to happen to make drones these multimeters for earth sciences. share the data. The moment nobody does, they stick it on their server and nobody ever hears from it again. Data standards. If I'm going to share my data with you, we better be talking the same language, same as every other field. And then data fusion tools, like the real power of drone data in science is going to be when we can fuse this data with other data sources. I literally last week submitted a proposal to NSF to develop all of those things with other people, not on my own. So fingers crossed, but if I don't do it, somebody is going to do it. Especially my age group, the next age group of scientists, maybe not so keen on this kind of use drones for science, but the next generation is coming up, like, we use drones to play as kids, we're going to use them for science. So I mentioned I've got this proposal in, hopefully we get to build all that stuff. But in the meantime, I'm developing what I'm calling SSEDD, this multi-snap stack that would make irises and phantoms and even your own hack drone that's running autopilot or PSD or whatever into a scientific tool. Come out of this open source community, so I'm going to have to rope in developers. But yeah, that's it. I don't have a question slide, sorry. Hope that was interesting to a bunch of embedded developers.
Thank you.
Yeah. I have a question for you. Is there anybody here who works in the academic sector? Ah, cool. I am jealous. Europe's regulations are way better. It's hard to do this in the US. In June, those commercial flight regulations here are supposed to get all shaken up, so hopefully things change. I'm really hoping science gets pulled out of the commercial sector. I'm not making any money on this.
Those already rumors that are delaying that further.
Sorry?
Those rumors that are pushing that back.
Well, the US is lost. That means we go and fly elsewhere. I'm actually from South Africa, so I'll just go home and fly there. Hence, that mate of mine is flying in New Zealand, not here. Any other questions?
I have one or two regarding, like, what you presented now seems to be mostly two things: a summary of your own work, which was quite interesting for us because it shows what sort of on the higher level of the stack is required to make drones actually useful and not just fun for some embedded developers,
yeah.
As you put it so nicely. And the second thing is that you seem to have uncovered a range of next problems to solve, in particular on the standardization side for data management. My question would be, you've covered a really broad range, which was, I think, a good thing for this conference because it sort of introduced us to a lot of those concepts. But going now towards a more, like, let's say, hands-on application, what is the current, you've introduced Snappy and other things, but what is the current workflow, if you can summarize that in a few sentences, that you're personally using from the drone, from mission planning, from post-processing? What are the tools you're currently using? What is sort of close to be useful?
Partly thanks to the FAA regulations here, at least, most of the people I know who are using drones for science are using a commercial company, which means it's all closed source, and it certainly doesn't have to be. The disaster management, recovery, rescue operation field has done some amazing stuff with open source techs out there. And so included in that proposal is to take all those tools that are out there, but they're hacker tools. They're not easy to use. They're command line GUI, non-existent, difficult to use. A neuroscientist couldn't use them. So to take all those tools and put them into nice, pretty packages. So at the moment, yeah, all of those images I showed you of actually processed data, it's all generated by commercial software. But it's because a neuroscientist doesn't have the time or the knowledge or the wherewithal to work out how to use open source tools. They are there. They're just a bit messy and not quite clean yet. yeah, personally, I'm using the open source tools, but I'm a lone engineer supporting a lone PhD student. Thanks to my position, I do have very strong connections into the science community. And so to do all that stuff that I've mentioned, to develop the standards, to develop the search and discoverability portal and so forth, it will be in conjunction with the earth science community. I'm not going to come up to them and say, yeah, look what I built. It's to work with them and develop it as they need it. But yeah, I can point you to web addresses that have a list of very cool tools, but they're messy, they're a pain to use.
I think it would be just interesting for us to see what people currently use on a detailed level. Okay, further questions?
EB is the commercial drone that my colleague is using. Esri is the big ArcGIS software company. They just licensed Pix4D to, they cover it in their own logos and whatever, but it's really Pix4D underneath good image processing tool suite. But yeah, all closed source. Even the data formats, like they're binaries. What am I going to do with that? So huge opportunity here. Again, I'm from Africa. I'm all for open source. I don't have 10 grand US dollars to drop on anything. But yeah, the only way I think this stuff is going to fly in academia is if we do open source it, if we don't get tied into commercial. You can't innovate with the commercial stuff. So cool. Thanks for listening.
Okay. Thanks for joining us.